Hello everyone, my name is Joshua Derivo. This is my lab for oscillations for class Physics 2211. The purpose of this lab is to analyze and model the oscillation motion of a mass attached to a spring in two dimensions. By using the position data from the real world and using that data to simulate a simulation of the spring attached to a mass, this helps us understand the law of conservation of energy. Here is the video of the oscillation. Now let's go over how we got the data into the tracker analysis. First, we imported the video into tracker, then we set the axis and scale by utilizing the calibration stick for precision. The center of the axis was set to where the spring was connected to, and then we marked the object position frame by frame to ensure accurate tracking. Here's the data from the tracker analysis. On the left is the first 10 positions on the x-axis and the y-axis. On the right is the full period between when the spring was released and the end of the video. Alright, now let's talk about the computational model code for the initialization part of it. First, the mass is set to 0.402 kilograms. The initial position is set to negative 1.21 e to negative 1 on the x-axis, while the y-axis was set to negative 6.32 e to negative 1. The spring constant was set to 6.83. The relaxed length of the spring is 0.123. K is the kinetic energy of the system, which was found by multiplying 0.5 of the ball mass times the magnitude of the ball velocity square. Then the gravitational potential energy was found by the ball mass times gravity times the ball position in the y-axis. The spring potential energy was found by multiplying 0.5 to the spring constant times the magnitude of the ball position minus the spring position minus the relaxing length of the spring squared, and the total energy was found by K plus the gravitational potential energy plus the spring potential energy. Now let's go over the code for the second part of the competition model. First, we store the initial energy, as you can see in the code. Then we set a gravitational force on the system, which is negative mass times gravity in the y-axis. Then we find the spring force, which is Ks times L hat. Then we find the net force by adding the force of gravity plus the force of the spring. Then we use the momentum principle to update the position and the velocity of the mass as it moves. Then we update the spring shape and the ball motion. Then we recalculate all the energies, and this is looped. Alright, here's our data set from the competition model. The blue line is the change in kinetic energy. The red line is the change in gravitational potential energy. The green line is the change of spring potential energy, and the orange line is the change in total energy. Alright, now let's compare the tracker data versus the glow script data. The tracker data is the red line, while the glow script data is the blue line. As you can see, the glow script data always reaches a higher point than the tracker data, both in the y-axis and the x-axis. This can be caused by two main reasons. The first one is the glow script data ignore a lot of stuff like drag, friction, air resistance, while the tracker data error can be caused by wrong initial conditions. Alright, let's talk about possible source of error. First off, we might be slightly off the true center of the mass, which will introduce small amount of errors. Moisture blur data made it harder to precisely track the center of the object while it was moving. And the spring has internal friction, which is caused by when it is overstretched or compressed too much, which will impact the data. And then we may incorrectly initialize the conditions of the system, which will set us off track. And then we did ignore a resistant internal spring dampening and friction. For the what does it mean question, yes, the model did satisfy the energy principle because the total energy stayed constant while the kinetic energy and potential energy were complementary, which means as one of them goes up, the other one goes down. Thank you for watching.